Today I shall start a new topic, which is remaining problem analysis. This is used during the design of hen. Now, while placing heat exchanger, many times we have more than one choice and we use these choices. Sometimes we find that the choices are taxing the heat exchanger area. That means, the area is increasing and it is becoming more than the minimum area computed by area target. So, out of the available matches, we should only select those matches which will not increase the minimum area calculated by the area target. Now, in this way, the remaining problem analysis helps the design. To guide the placement of the heat exchanger in above and below regions of pinch, so that the targeted values computed by the targeting procedures are not increased to a large extent. The targeted values in this case are energy target, number of units target, area target and the cost target, and this can be used for remaining problem analysis. Now, let us see it through an example, which is given in table 6, a 4 stream problem which we have also taken earlier, and apply this remaining problem analysis to this. So, we start a new problem. So, we add streams H1, the supply temperature is 160, the target temperature is 60 and MCP is 2.5. This is necessary to start the problem from the beginning, because then only we will be able to show the concept of remaining problem analysis. H2 140 30 and this is 1.5. Add, this is C1, this is 20, the target temperature is 125, the NCP value is 2, C2, $80, 130 and 3.5. I am using the default values of hot utility and cold utility given in the software hint. It is also possible to define these utilities and do the remaining problem analysis. So, this is the grid diagram which I get for this stream table. Now, we have to place heat exchangers. So, the first heat exchanger we place, because the first heat exchanger is a pinch exchanger, we go via this route, feasibility above pinch. So, here the MCP hot stream is less than MCP cold stream. So, this can be matched with this. So, I place a heat exchanger. Now, once I place a heat exchanger here, then I have to go to the heat exchanger drop down menu and press the remaining problem. Now, this dialog box opens. It tells that the minimum number of heat exchanger is 7. I have installed one heat exchanger and the remaining is 5. So, 5 plus 1 is 6 and here it is 7. We have to understand why this has happened. Here in this problem there is a subset equality, and that is why the number of heat exchangers will be 7 minus 1 equal to 6, and that is why it is showing 6 heat exchangers. Now, it tells that the minimum area required using the area target is 21.9533. I have installed one heat exchanger, its area is 961286, and the area of the remaining 5 heat exchangers are estimated to be 12.4024. If I add those two quantities 9.61286 and 12.4024, it becomes 22.0152. That means the total value has exceeded the minimum area required by a little bit. After finishing this problem, we will see that in a tabular form that how much area has increased and why I have accepted that match. Here you see that there are 4 things given: area, capital cost, heating and cooling. These 4 quantities can be used for the remaining problem analysis. However, I am only using the area part of it to demonstrate the remaining problem analysis. You can use any of these 4 to the remaining problem analysis. Now, I put the second heat exchanger. So, again the second heat exchanger is a pinch heat exchanger. So, it can be easily put through this. So, this and this, I click this. So, this is the second heat exchanger I have put. Now, after I have put the second heat exchanger, again I will go to the heat exchanger menu, go to the remaining problem, this dialog box opens. Now, here the area target remains the same, but installed are 2 heat exchangers and the total area consumed by these 2 heat exchangers are 14.4784, and the remaining 4, the area of the remaining 4 heat exchangers are 7.5368, and the total is 22.0152. So, the total has not increased, almost remains same as before. So, we can accept this heat exchanger. Now, we go to the stream feasibility below pinch, and here the MCP hot should be greater than MCP cold. So, I have to match this and this. I can put up a pinch heat exchanger here also. Then again I go to the heat exchanger menu, remaining problem analysis, and open up this dialog box. It says that the area target was 21.9533 unchanged, it will remain unchanged. We have installed 3 heat exchangers and the area, combined area of all the 3 heat exchangers is 20.0746 and the remaining 3 are 3.02272. The area has increased a little bit to 23.0973 and the increase is about 5% or so, but I have nothing, no options. So, I have to act. Then I go for the heat exchanger, add and put up my 4th heat exchanger between the number 2 and number 3 streams. So, add 4th heat exchangers. So, my cold is number 3 and hot is number 2, and the enthalpy of this heat exchanger is 45. My cold inlet temperature is the cold supply temperature and hot inlet temperature is my pinch temperature. So, I say OK, it puts a heat exchanger here. Now, I again go to the remaining problem analysis. It tells that 4 heat exchangers have been installed. The combined area of the 4 heat exchangers, installed heat exchangers, are 21.1057. There are 2 heat exchangers remaining. We know that cooler and heaters are remaining, and the area, combined area of those 2 heat exchangers, remaining heat exchangers, are 1.99162, and the area is almost constant as before, that is 23.0973. So, we take it OK. Now, we will place the heaters and coolers. So, here between this we have to put a heater, because the cold stream, which is at 117.5 degrees centigrade, is to be heated to 125 degrees centigrade, and we have to use the hot utility for its heating. Similarly, the hot stream, which is at 60 degrees centigrade after the heat exchanger 4, has to be cooled down to 30 degrees centigrade, and hence it needs a cooler, and we have to use the cold utility. So, let us put the heater here in the stream number 3. So, again we go to the heat exchanger, add, here we use add this 5th number, then cold stream number is 3 and hot stream is utility, and the enthalpy is 15, and the cold inlet temperature is 117.5. So, if I say OK, it puts a heater. It puts a heater here, and this heater hits this cold stream from 117.5 to 125, and its capacity is about 15 kilowatt. Now, we have to put a cooler here. So, we go to yes, after putting the heater, we again go to the remaining problem analysis. Here we have put now 5 heat exchangers. The combined area is 21.2294, and there is one remaining, that is the cooler, which area is 1.64972, and the total area combining this remaining and installed is 22.8774. So, we see that it has decreased, and hence the increase in the area has also reduced. We will see that later. So, we can accept this heat exchanger. So, now here we have to place a cooler. We add this, we put the add. So, it is a 6th number, cold stream, cold utility will be used, and hot stream is number 2, and enthalpy is 45, and the inlet temperature, the hot inlet temperature is 60. So, we place this . Now, we again go to the heat exchanger menu, remaining problem analysis. We see that here we have installed 6 heat exchangers whose combined area is 22.692, whereas through area target we get 21.9533, and the total area after the design is about 22.2692, which is quite close to the area given by the area target. So, this design can be accepted. Now, let us see the analysis part of it. Now, the area computed for above and below pinch using area target was 21.9533 meters square. Number of heat exchangers using units target, and when we are calculating this number 07 number, we have used this units target above the pinch and the below the pinch, and then we have joined the results what we got. So, it becomes 7, but there is a subset equality in the problem. So, one subset equality, and that is why the number of units will be decreased by 1. So, 7 minus 1 is 6, and what we saw in the remaining problem analysis that it calculated 6 units. So, the heat exchangers which was put between stream 1 and 4, which was heat exchanger 1, has a load of 175 kilowatt and its area was 9.61. So, the total installed area was at that time 9.61, and the remaining area of 5 heat exchangers were 12.4024, and the total area was 22.0142, which was 0.28% excess or more than the targeted area of 21.9533. So, the match is acceptable. In the second match, which was between stream number 2 and 3, which was heat exchanger number 2, the load of the heat exchanger was 75 and the area was 4.8655. This was computed, or this can be taken from the other menus, like I will show you here. We can go to the heat exchanger menu, we can go for the results, and we can go for area and cost. Here I find the area of the first heat exchanger, then I can go to second, here the area of second heat exchanger, I can go to third, fourth, fifth, sixth. So, this way I can have the area of all the heat exchangers. Even if I want cost of heat exchangers, I can have from here. So, we again go to this. So, the area of the second heat exchanger was 4.8655, total installed becomes 14.4784. This shows the area of this heat exchanger plus this heat exchanger, and the remaining were 4 heat exchangers whose area was combined area was 7.536 The total area is 22.0152. So, increase is around 0.28% and hence the match was accepted. Now, when we went for the third match, which was between stream 1 and 3. So, due to the pinch rules, we have to accept this match because this was the only match which is feasible. So, its load was 75, the area was 5962, the area of combined all the 3, that is this, this and this, was 20.0746, and the remaining area of 3 heat exchangers were 3.02272, total was 23.0973. Now, this showed at 5.2 increase, 5.2% increase than the minimum area which we got through area targeting. So, this increase is considerable, but we have no option because the pinch rule says that we have to accept this, and this was further, this was a pinch heat exchangers. So, we cannot violate the rule, hence we have to accept this. Then we place the fourth heat exchangers. This exchanger also, this exchanger violated the pinch rule, but when we compute the delta T minimum, it did not violated the delta T minimum criteria, hence it was accepted, because the pinch rules has to be followed strictly if the heat exchanger is a pinch heat exchanger. So, here when we put the fourth heat exchanger, the area comes out to be 1.0311. The total area of all these 4 heat exchangers are 21.1057. The area of the remaining heat exchanger, in this case there are 2 heat exchangers remaining, the heater and the cooler. It combined area is 1.99162 and the total area is 23.0973. So, there was an increase of 5.2%, but I have no option, I have to accept this match. Then we put the heater and coolers. So, this is the heater, this is hot utility and third number of stream. So, its load is 15, its area is 0.1237. The total area of this 5 heat exchanger is 21.2294 and the remaining area, that is the cooler's area, is 1.64792 based on the remaining problem analysis, and the total area is 22.8774. Now, we see that little bit the area decreases to 4.2%. So, the match is accepted because I have no option, and then I put the cooler, which load was 45, the area was 1.0398 and total installed area of all the 6 heat exchanger is now 22.2692 and there is no remaining heat exchanger, that is why this is 0 and the total area is now 22.2692. So, this shows a mere increase in the area by 1.4% and hence the match is accepted. So, what we found that after the design, the area has slightly increased than the targeted area and this increase is 1.4%. Now, this shows clearly how the remaining problem analysis can be used. Let us take another example of remaining problem analysis. The problem is given in table 7. There are 2 hot streams, 2 cold streams and user defined hot utility and cold utility. Now, if we plot this using the software, then we get the stream data like this. This is the user defined hot utility H1 182 179 and this is user defined cold utility from 20 to 30 and these are process streams. Now, we will apply our process, we will apply the remaining problem analysis technique for the design of heat exchanger. Now, if we go to the streams and feasibility and see the feasibility matches, then we see that above pinch there are alternative matches available. There are many options. 3 can be matched with 1, 3 can be matched with 2, 4 can be matched with 1, 4 can be matched with 2. When we go for all these alternatives, then we find that these alternatives tax the minimum area, targeted area differently, and thus we should select those matches which taxes the minimum area by area targeting less. This we will see through this example. Now, let us put a match between 1 and 3. 1 and 3 match is perfectly possible. So, we go to the feasibility above the pinch and we here see here that 1 and 3 match is possible because MCP of hot stream should be less or equal to MCP of cold stream. This condition is satisfied. So, we put this match. Now, this match is of 10,000 kilowatt, and if I go to my remaining problem analysis, what I see that I have installed one heat exchanger. Its heat transfer area is 13,333.3. My area from area targeting, I get area of 22,668.2, and when I place this match, the overall area becomes 27,824. And if I see this taxing is about 22.7%. So, this is 22.7% more than the area target, and hence this match is taxing a lot, and hence it should be removed. So, I select this heat exchanger, I go to delete heat exchanger number 1, I delete it. Now, the next match I should put between 1 and 4, because this is a acceptable match. 1 and 4, this is a acceptable match, perfectly right. So, 1 and 4, it also allows me to put that match. So, I put the match. So, this match is of 15,000 kilowatt, and if I use the remaining problem analysis, so what I find that the match, the area of the heat exchanger number 1 is 9,241.96. My area targeting gives me area of 22,668.2, and the average area is here 22,726.6. So, it is quite close to the area of the area target, and if I quantitatively find out, it is only 0.257% more than the area target value, and hence this heat exchanger is acceptable and this is a good match. So, we did not go for the first heat exchanger because it taxed us about 22.7%, and this heat exchanger is taxing only 0.257%, and that is why we have gone for this. Now, we put the second match. Streams, visibility, above pinch. Now, the second match can be between stream number 2 and stream number 3. So, we put a second match. Now, after putting the second match, we can go again to the remaining problem analysis. We found that we have already installed 2 heat exchangers. Their combined area is 13,148.3. Area target, from area target I get 22,668.2, and the remaining 4 heat exchangers it is 9,578.28. Now, the total area is 22,726.6. We will find that in this problem there are two subset equalities are there, and hence the number of heat exchangers which we will be installing will be less than the minimum number of heat exchangers 7, which has been calculated on the basis of units target without considering the subset equality. So, this heat exchanger, that is heat exchanger number 2, is only taxing me 0.257%. That means, the total area is 0.257% more than the area which has been targeted. So, this is acceptable to me. Now, we go for a third heat exchanger, and that third heat exchanger we will put here, below pinch, and I would like to tell you that if you see the feasibility matches, there is only one match available in the below pinch, that is stream number 1 and stream number 3. There is no other match. So, I am bound to put this match. So, when I put this match 1 and 3, so when I put this match 1 and 3, I again run the remaining problem analysis. So, altogether these 3 heat exchangers is contributing 23,148.3, and there are 2 remaining heat exchangers which are 1992.05. So, the area immediately jumps up to 25,140.4. Now, this is about 10.9% more than the targeted area, which is 22,668.2, but I have no option. So, I am putting up this match. This is costing me 10.9% more area. As I have no alternative, I am accepting this match. Now, then we have to put heaters and coolers, because 2 heat exchangers are left with. So, let us put a heater which is obviously to be put between the H1 and the stream number 3, this, because this temperature is 102, it has to be brought to 110 degrees centigrade. So, heating is required. So, we go for heat exchanger, add heat exchanger, hot stream we go for U1, that is user defined hot stream number 1. Here I have to select the 3, that is this stream, and then I go for user supplied enthalpy. The enthalpy is 2000 in this case, and the cold inlet temperature is 102. So, here I have to go for 4th number. So, again I have to change, this is U1, this is 3rd, this is 2000, this is 102, and then I press OK. So, let us see what has happened. Oh, again I put the heater. So, add. The mistake was that I did not selected it properly. So, this is fourth number, this is third stream, and this is U1, enthalpy is 2000 and inlet temperature is 102. So, I put it here. So, this is the heater. Now, if I run the remaining problem analysis, it says that we have already loaded 4 heaters, 4 heat exchangers, and the one heat exchanger is left with, and this has become 2409.72.4. Now, we put the last heat exchanger, which is C5, which is between the cold stream and this stream number 2. So, we go to the heat exchanger, add menu, then we change this to 5, and this is cold utility U2, and this is hot stream is 2, and its enthalpy is 4000, and hot inlet temperature is pinch temperature. So, let us OK. Now, if I see this remaining problem analysis, it shows that the area is 2400 24219, and there are 5 heat exchanger has been installed. And why this is 5? Because if you see, this and this forms a subset, and this forms a subset, and as there are 2 subsets available, the number of heat exchangers required is now 7 minus 2, which is 5. So, we get 5 heat exchangers here. So, what we conclude that, and this area if we see, we can calculate 24,219 minus 22668 divided by 22668. It is about 6.8% more. It is about 6.8% more. So, we have to bear with this 6.8% more area for this heat exchanger. Now, what we observed from here that the remaining problem analysis in a complex situation helps us to place the proper matches which will not tax the area of the heat exchanger network. Now, I will explain what is the role of driving force plot. We have seen that if we have options for different matches and we exercise this option, the area of the heat exchanger network changes. Now, the question is why it is changing. If we start probing this question, then we will find that different heat exchanger networks utilize the driving force which is available for heat exchange in different ways. That means, if I consider available driving force is 100%, then some network may utilize 90% of it and some other may 70% of it. So, if a network is utilizing 70% of the driving force, its area will be higher. If it is utilizing 90% of the driving force, the area will be less. So, different heat exchanger network design offers different area. This we will try to understand through a small problem. So, this is the problem we will take, a 3 stream problem to demonstrate driving force plot, 2 hot streams and 1 cold stream. So, we go to stream, add, this is H1, supply temperature is 180 and target temperature is 140 and MCP value is 2, add H2, supply temperature is 165, target temperature is 105 and MCP value is 4, add C1, supply temperature is 80 and target temperature is 144 and CP value is 5. Now, this is the composite curve. So, if I take the composite curve, that means this is the hot stream, this is the cold stream, and when hot stream is giving heat to the cold stream, the temperature difference is this much. For this place, this temperature difference is this much. For this place, this temperature difference is this much. That means, the driving force which is available is shown by the distance between this and this. If I go to the diagram and place this available temperature difference, then this plot I get. The distance between this and this is shown, shows the driving force which is available. So, here I see the distance between this and this is equal to the distance between this and this. This is the composite curve and this is the driving force plot. The distance between this and this is distance between this and this. Now, when we place heat exchangers, if the heat exchanger utilizes this driving force nicely or properly, then obviously the area of the heat exchanger will be less, and if it is not able to utilize this driving force properly, then area will be more. So, we have to place the temperature profiles of the heat exchangers on this driving force plot, and then only we can know about this. If we take a second problem, say this, and solve it with hint, we get a driving force plot like this. Here the driving force is less, this is shown here, and basically the driving force plot is between the temperature of the cold stream versus the temperature of the hot stream. And in this plot we are measuring the driving force from this diagonal line upward. Thank you.